For our next example, we have that the table shows the results of a survey that asked 3,203 people whether they wear glasses or contacts. And we want to find the probability that a randomly selected person from the sample wears either only contacts or only glasses. Well, looking at this, it's a contingency table problem like what we saw with the multiplication rule. But in this case, we're not given any conditioning that says this given something else. We are just specifically looking at groups where we want to find this probability. What we're looking for is the probability of either glasses or contacts. And I'll say that yes, there are people that wear both, but for the sake of this, since they are saying only one or only the other, they're tossing out that both case specifically in the wording. What we're going to do is recognize that these two events are disjoint. You can't have only one and only the other. It's the defining property of the word only. So, we have the probability of only glasses plus the probability of only contacts, where glasses is 253 over 3203 plus 1268 over 3203, which adds up to a total probability of 1521 over 3203, or if you prefer, about 47.5%. So that's about a 50-50 shot based on this empirical data that you will get someone who wears only glasses or only contacts. To get one more example of this stripe, we have that a blood bank catalogs types of blood, including whether they are positive or negative, given by donors in the last 5 days, where the number of donors who gave each type is shown in our table. And we want to find the probability that the donor that we select, a randomly selected donor, has type B blood or negative. Well, for this, we're looking at the probability of B or negative. What we have to understand here is, again, we're doing contingencies, but there's not so much given things. Again, we're going to look at the type B's, that column there. And then we're also going to look at the row for those of which are negative. And we're going to see that in there, the row and the column do have an intersection, that there are 8 people who donated type B blood that is negative. So as a result, when we're counting the type B bloods, we're going to get those 8 people. And then when we count the negative blood, we're going to get those people again. So these events are not mutually exclusive. They are not disjoint. And when we take the probability, we've got to get rid of that overlap. That is, we want the probability of type B blood plus the probability of negative blood minus the probability of B negative blood. Because B's and B, negatives and negative, we don't want all of that. We've already got enough. So here, we're going to have 45 of our subjects with type B blood out of 409 total, plus the 65, oh man, that 5, out of 409 total, minus the 8 that we don't want, because we've already got some of them here and some of them there. We don't need too many. And if we add that up, subtract out our 8, we'll get 102 out of 409, or about 25%, 0.249, where this tells us the probability of getting someone with type B or negative blood is about 25%. And I'll say that there are a few more examples for this type of thing in the PowerPoint if you want more work. There's also examples in the book if you want them, and I'm sure you'll get practice from this stuff in class and with the homework. But essentially, once you get the idea of what you're looking for, there's not a great deal of subtlety to these types of problems. Anyway, that's what we're going to see for section 3.3. The last thing we're going to get from chapter 3 is stuff in 3.4 talking about counting methods, which may sound like there's not much to it, but there actually are some interesting things going on there that we'll see next.